Hello everyone, I'm Spanker from Kaiser Power Electronics, and today I would like to show you another Ericsson radio base station system. This is the RBS6000. It is the successor to the 3000 system that I showed you in the last video. This system, I do not have the complete system, but I have a 2.6 GHz 40 watt power amplifier module that I will show you, take apart. This particular amplifier can run both GSM, CDMA, VDCMA and LTE, which is the two last are the 3G and 4G networks. The amplifier itself is the radio unit 01B7. The RBS6000 could be configured for 2x6 of these amplifiers, so I think roughly that's about 20,000 connected users if the cabinet is filled up completely, but that would only be for one technology. This can run single mode or mixed mode, so you can choose between the different network technologies, whether you want to run a lot of GSM sectors and antennas, or you can run fewer at a higher speed with the 4G and 3G networks. But let's take a look. So here we have the unit itself. As you can see, it's rather large. It is a 40 watt amplifier. We have the power input, we have the data connections, 2 optical inputs. There are 3 status LEDs. There is a receive input output, there's a receive out, and receive B input output. And then there are the 2 antenna connectors for the transmitting part. If we take a look at the side of it, we can see the whole diplexer assembly sits here. This heatsink is for the amplifier, the transmitting amplifier. And if we look at the position of the receiving outputs, it's pretty clear that the logic for all this is behind this heatsink. So it is rather modular built with all circuitry over in this part, diplexer, power amplifier. So let's take a look inside. So let's take a look under the lid. Okay, that is the back side of the RF PCB. We have the receiving output here. It's pretty clear that we have a couple of large CPUs. Another one there, another one here. And up here behind the power amplifier part, we can see a lot of ground stitching around the RF connectors up to the diplexer. And this is perhaps the receiving, since they sit back here, so maybe this signal route goes all this way. But let's take a look and see if I can pry this open. Yeah, that was not so bad. Comes off in one piece with only the connectors to the diplexer as expected. And if we take a look, we can see that we have all the receiving down here, the 2 connectors to the diplexer, and at the over here we have all the power supply part, a lot of ICs for the transmitting and receiving, encoding, decoding of signals. And then up here we have, let's see, DC input, some more power supply, more power supply. But over here it connects to the power amplifier, so this is probably a splitter preamplifier. This also connects to the power amplifier. So these two could be two different technologies, but I will of course take high resolution pictures and explain all this circuitry later. Now let's take a look what's at the power amplifier and then the diplexer. Up here we can see the connectors to the power amplifier, and down here the connectors to the diplexer, to the receiving part of the PCB we just took a look at. So with all the screws removed, let's take a look at the power amplifier. Comes off in a one nice piece. Really nice modular system they made here. So it's pretty straightforward, really, when you have seen a couple of these amplifiers inside. There is two channels, as there is two antenna outputs. Goes up through splitting, preamplifier, power amplifier, circulator for the. Okay, now I don't. Okay, this was connected with a bridge cable at the front to the diplexer. So once we look inside the diplexer, we can see what this actually connected to. And up here we have a power supply for the dual amplifier. It looks like the tracks are identical for both amplifiers. So it's not made especially for using one technology at one and one at the other. But both are probably capable of yeah, oh wait, this was only a 2.6 gigahertz amplifier, so this is of course a 2-channel 2.6 gigahertz amplifier. But I will also take some high-res pictures of this, and we will walk through the circuit later in this video. Now let's take a look inside the diplexer. So with a hell of a lot of screws removed, we can now take a look inside the diplexer and see how that works together with what we saw at the power amplifier part and what's inside here. At first up here we have, seems there's some unpopulated board, and there's a little circuitry here, but not much, just looks like input protection. Up here we can see that we have some large adjustment screws and some smaller. These are used to tune the cavities that we see here to the exact frequency to be used and filter out other frequencies than the 2.6 gigahertz that this amplifier works at. Now this is pretty interesting because I have not yet seen an amplifier or diplexer with an interior like this, where the these tops are made of what looks like a plastic or composite material. I have only seen this made from metal, both ferromagnetic or brass or silvered brass or such. But this is new to me. It's that's the fun part of this. Every time I take a diplexer apart, it's something different. But now, if we take a look at the power amplifier, we had the two inputs to it here: preamplifiers, power amplifiers, circulator, output. This output was connected to this. It goes all the way through here, up here, and then through this cavity here to the output. And then this antenna can also receive on this channel, where it connects over here to the main control board. But the other antenna down here looks like it's only a receive antenna, because there is no connections to the transmitting part up here. So, but this is just mounted with 4 screws to the frame itself. Not so much special about that. The top plate with the adjustment screws, as we can see, the tiny ones, which are in between the plastic tops down here, are silvered brass screws, but the large ones are just rough, regular brass. Doesn't even look like it has a special nice finish to it. So next I will explain the circuit and signal path via some high resolution pictures taken of all these boards over here. So let's take a look at that.
Here in the overview of the main circuit board, we can in the middle and top see the bus connectors along with the DC power supply connectors in the right side. The Ericsson CPU ROB101 1190/2 named AUC is the board processor. This goes into the main processor cluster, which was introduced in the radio base station 3000 system and is also used in the 6000 system. It sits along with 128 megabyte of SD RAM. There is also a Xilinx Vertex 5 FPGA to handle different monitoring of the board, but other than that, this Ericsson CPU, the AUC, handles all the monitoring, and if this CPU fails, other board processors in the main processor cluster can take over the monitoring of this board, so it can actually continue to function if only some part of the CPU fails. The two Ericsson ASIC ROB101 089/3, the Warp1 processors, we have 2 of those at the left side of the board. These are the back-end translators from the receiving part of the board. These 2 CPUs translates the analog to digital converted signal back into the telecom protocols. This will be the next step, next circuit part that we take a look at. Down in the right corner of the picture we can see the Altera Stratix 3 FPGA. This handles the protocol, the telecom protocol decoding into a digital data stream that is then converted from digital to analog down in the transmit part, which we will take a look at after the receive part. Looking closer at the receiving part, we will see that we have the 2 connectors here in the left side marked with yellow. There is a lot of white hybrid couplers that sits all around the board to split out the different phases of the signal into various measuring equipment. The first big one is the Amplifier Singer 1P63S coupler, and we have a what I assume is a Philips preamplifier sitting here. It's an unknown IC marking, so I have not been able to look that up. The next we have is an Analog Devices OP747, which is a precision micropower op-amp. Along with the Max 10-channel 10-bit system monitor, these are both a part of the whole system monitoring system. The analog signal is then routed on from the Amplifier Singer coupler that we saw at the start, or from the Philips CPU, up on through somewhere along the board to the Max 19997 down conversion mixer. The Max 1997 down conversion mixer uses the Analog Devices ADF4153 4 GHz local oscillator, which at this point I guess it's clocked at 3 GHz. As we can see on the illustration down in the left corner, a down conversion mixer works as follows. It has a local oscillator, and it takes this local oscillator frequency and minuses the RF carrier frequency, which is the 2.6 gigahertz that we have in this amplifier. And to be able to feed a 400 megahertz signal on to the analog parts that lay ahead, this simply down converts the 2.6 gigahertz to a 400 megahertz signals by imposing the waveform onto a lower carrier frequency. In order to not lose any bandwidth when downsampling from a high frequency carrier to a lower frequency carrier, I think that the Analog Devices ADF4002 phase detector and frequency synth, along with the Analog Devices AD9510 clock distribution system, simply clocks the signal into the triquint 358 megahertz SAW filters. If we take a look at this other illustration, we can see that a SAW filter is a mechanical isolation type, so you can separate signals from each other and have complete electrical isolation. The SAW is a short of surface acoustic wave filter and is made up of a transducer and a piezoelectric element and then a receiving transducer, so you can put in a current, and the mechanical waves induced by in the piezoelectric element induced by this current results in a voltage in the output transducer. This provides a high isolation voltage, but it is also incredibly efficient at up to 99.99% efficient. So it's very hard to beat this filter and isolation technology with any other part. From the triquint SAW filters, the signals are fed onto the Skyworks Sky 73084 mixer, which, along with the Analog Devices ADF4110, the 550 megahertz local oscillator, again is split out and down converted out to the two adjacent ICs at the Skyworks mixer. I'm not sure of the frequency it's down converted to this time, but we can also see it passes through two passive filters before it comes over to the two linear technology LTC 2208, which are 16-bit 130 megasamples per second analog to digital converters. The two Texas Instruments differential line receivers are simply providing impedance matching and isolation and level matching, signal level matching, and so on, down to the two Ericsson ROB1 CPUs that we can see down in the left corner of this picture. At the transmitting part of the board, we have two Texas Instruments digital to analog converters, which are the DAC 5686, which are dual channel 800 megasamples per second 16-bit DACs. These signals from the analog signals from these are then converted through the ST Microelectronics up converter mixers. I have not been able to decipher these part numbers and find any data sheets on these. So I have just mentioned the names of the ICs on the board. And these signals are then, when up converted to 2.6 gigahertz, routed on to the power amplifier module, which we will take a look at next. Looking at the very beautiful power amplifier module, it becomes apparent that this board can be used for many different frequencies and possible different transmitting receiving technologies. As we can see, there are many unpopulated parts of the board, and this basically tells us that it's a board used for many different designs or amplifiers. Starting in the right lower corner we have the two inputs from the transmitting part of the large PCB. There are two small preamplifiers before entering the Freescale SW7IC 2725GN preamplifier chips, which are the black ones seen in this picture. As we can see, there are many unpopulated tinned points along the power supply lines and filter lines, and how far out a capacitor is placed could have to do with the frequency chosen for this current amplifier. So it could be that if the SMD capacitors were moved closer to the ICs, it would be a lower frequency filter for a lower frequency amplifier. From the black Freescale preamplifier, the signal goes through a small silver colored circulator with a blue resistor sitting at the third port. This is simply to isolate the preamplifier from the power RF MOSFET, which are the NXP MRF7S27138S N-channel RF MOSFET. This is a 2.6 GHz 105 watt CV continuous wave power amplifier. The gold tracks that we can see from the circulator and into the MOSFET, these funnel-like and also box-like parts that we have on the tracks, these are actually low pass filters, and we can see that the power rails are also supplied through quarter wavelength parts, these bent tracks that goes out to the decoupling capacitors. When a quarter wavelength filter is used this way, it will present a short at the wavelength and the half wavelength and DC, but anything above this will get short, or will get filtered out because it's seen upon as an open circuit for through this filter. As we can see, there are two parallel lines which are combined again. I'm not sure if this is because it's a Dorothy amplifier or maybe it's just a phase shift. The combined outputs from the two power amplifiers goes through the Anoren Singer 2 hybrid coupler and is phase shifted before going through the circulator. As we can see, the signal enters at port 1 and goes out at port 2. But any RF energy going backwards into port 2 would get routed down to port 3, which is the black attenuation resistor sitting at the bottom of the circulator. And thus no signal is allowed to go back into port 1 from the antenna connector. The last gold track that we can see at port 2 of the circulator is actually a quarter wave stop, which is another filter, but it is not connected at this configuration of the amplifier, but it would be a quarter wave filter, possibly to filter any incoming noise back into the amplifier. I hope you enjoyed watching this video and learn as much as I did taking this amplifier apart, and just looking at these nice power amplifier pictures here at the end. I hope you will subscribe to the channel, come back later for more teardowns, more high voltage videos, and what else that I have coming up. So stay tuned, hope to see you later.